Right, let's go ahead and get started then. So yeah, how to build a linguistic time machine. You're probably wondering what the heck this is all about. So what are we talking about here? So a bit of background. Um, we're discussing this concept that we're well aware that there are lots of things in our lives where we can say that the only constant about them is that they change. But as linguists, we're especially aware that this is the case for language. So language is not static, it is ever changing and dynamic, not just in the synchronic sense, but also in with regard to this talk about sound change with regard to a historical sense. So we are aware that language sound systems change, but we're still not fully aware why they change. And the ultimate question is, you're understanding me right now. I'm using language, I'm using speech to communicate my thoughts to you, and those thoughts are entering in your brain and being decoded. That is a stable system. And if language is stable enough to promote communication in this way, why should it ever change from that state? This relates to what's called the actuation problem of sound change. So the idea that there are certain mechanisms that can serve as catalysts to sort of introduce change into a system at the very sort of level of introducing those seeds before it's diffused. So that's what this topic is about, is the actuation problem. What sort of mechanisms can serve as those catalysts? So in broad terms, there are sort of two different ways of approaching sound change that comes from the speaker and sound change that comes from the listener. And there are lots of different types of sound changes of the first kind, speaker-based. So I give an example here of a well-known and very common sound change of palatalization of velars before front vowels. And I'm sure, as all of you are aware, you could write out rules for this and explain why this is the case and really talk about how the limitations of the vocal tract in time sort of lead to this change happening where the back of the tongue moves further and forward as, you know, or in anticipation for this front vowel for the position it needs to be in. So it's easy to sort of explain this in terms of speaker-based sound change or some sort of interaction of speaker and listener. But then we come to examples like this, alternations between, for example, velars in Proto-Indo-European, and which later changed to labials. Now, the reason why the example above palatalization, this constraint makes, I mean, this physical constraint makes sense because there's one articulator that's sort of sharing resources over time, right? So the tongue can't split into two and be in both places at the same time. But sound changes like this alternation between velars and labials, we can't really understand these in the same way because there isn't any constraint. There isn't any constraint on the system because there isn't a physical link between, for example, the back of the tongue and the lips. So we can't really readily explain this as a speaker-based sound change. So we think that it's probably listener-based. Now, we say that, and that's sort of, you know, it's easy to say, okay, well, it's based on the listener. Something happens, and they hear something, and then go on and produce some sort of new variant in the system. But we have to talk about then how that might be the case, right? So we have this simple sort of speech chain model where the speaker has some idea in their head, and then they have some sort of articulatory plan to then get that encoded system out. And then that has an acoustic effect. Then that is perceived in first the auditory system and then the mind, decoded in the mind of the listener. And then if that listener were then to recreate that sound and sort of play a part in this thing that we call language and communication, then they articulate what that thing is that they think that they heard, right? So this is simple enough if we consider an articulation acoustics perception change in this way, where there's this just kind of goes around and you say something and that has acoustic effects and somebody else hears that and then they articulate the same thing and so forth. But in a system like this can't account for this fact that language does change. So if the chain looked like this, there wouldn't be any way for that chain to sort of break down. Well, this is because the chain doesn't look like this. The chain more looks like this, where there are many-to-one mappings between one level and the next at each of these different interfaces. So a lot of the work that I do is on each of these individual interfaces or each of these individual nodes, but then the interface between them. So how speech is articulated. This is me here in MRI. And then the relationship, the sort of many one-to relationship between how can multiple articulations then lead to either singular or multiple acoustic effects. Then sort of deep dive into what those acoustic effects are, how to analyze them, how to understand them in terms of speech systems. Then what is the many-to-one relationship between these different acoustic effects and how people might perceive them? And then today, I'm going to sort of talk about sort of an overarching research program that I've been working on for the past several years that kind of links all of these together. And so I'm going to present work from, well, it's been a few years ago now, but like I said, this is ongoing work. And hopefully this year I'll be submitting a grant application to continue this work. But this is based primarily on these three articles from these journals. So the thing that I'm going to talk about in particular, the phenomenon that I want to discuss here is vowel nasality. This is the thing that I've studied the most, the thing that I really still like studying, in part because it is so difficult and it is ripe for these many-to-one effects, which sort of gives the ability for that chain to break down. So what is it about vowel nasality that's so interesting? Well, let's first take a step back and kind of talk about how we sort of approach nasality in Linguistics 101, or how we might sort of assume that nasality is realized in some sound system. So vowel nasalization itself is characterized by coupling the oral and the nasal tracts when the velum is lowered. We just call this nasalization. And of course, in the IPA system, we use a tilde as a diacritic above some sort of vowel sound that gives us then the nasal vowel sound. But this has the implicit assumption that the underlying, all the characteristics of that vowel, whatever they may be, are the exact same. So we have an epsilon here, and then we have an epsilon with a tilde over it. That still implies that everything about that vowel is the exact same in all aspects but the state of the velum. In other words, for example, the oral cavity for un remains the same as for e. This is sort of a binary perspective of what nasality is. The velum kind of acts like a trap door and opens and closes, and that's it. However, there's lots of research to show that this really isn't the case, that lowering the velum is just one of multiple different articulatory characteristics that can be used to distinguish nasal vowels from some oral counterpart, or for a nasal vowel system from an oral vowel system. And in particular, this question about the state of the oral cavity is really interesting because it's been found in work that I've done and work that other people have done in both phonetic and phonological vowel nasalization. There are differences in tongue configuration when you compare these sort of assumedly same vowels that are only changed with respect to the velum. This isn't the case. There are changes with respect to, could be the pharynx or shape of the tongue or even configuration of the lips. So tongue height in particular is sort of problematic when it comes to vowel nasalization because, as we know, there is a relationship between F1 and vowel nasalization, inverse relationship. As the tongue lowers, as the jaw lowers, F1 increases. We all know this from introductory acoustics. And this is what we normally think of when we talk about changes in F1. Oh, there must be a change in tongue configuration. So vowel nasality provides a really unique problem. There are acoustics associated with the oral cavity that we think we somewhat know well. However, there are acoustics associated with the nasal cavity as well. It's also a resonating cavity in the body. And unlike this diagram, which just depicts it as this big open space, it is far from that. Physiologically, it's a very complex system inside of there. And the acoustics are far less well known than what we think and we know about acoustics associated with the oral cavity. We even know less about what happens to the acoustics when these two things are combined. So vowel nasalization conflates the effects of both of these channels. However, once the acoustic signal reaches our ears, or in our domain as we're analyzing, be it formants or whatever we want to analyze about a vowel system, once that acoustic signal hits the microphone, there isn't any way to tease that apart. Those acoustic effects are conflated as soon as they hit the atmosphere, and that's it, right? So the question then is, if you measure some sort of effect of F1, how do you know whether it's due to, for example, changing the tongue or nasalization? So in 2018, I did a study where I tried to tackle this problem. This is something that I've worked on for many years, and this is the closest I think I've come to being able to at least get some sort of knowledge about what is the independent effect on formant frequencies when the velum lowers, right? So what I did, sounds like a really weird study, but I had 6 different trained phoneticians, all different language backgrounds, and set up this this sort of contraption where I had an ultrasound probe holder underneath the chin that was tracking the shape of the tongue, and then also what's called a nasal instrument or a nasometer. And it's actually a really simple system that works quite well. As you can see here, there's a you can't really see the whole size of it, but there's this acoustic baffle that sort of like goes to the past the edges of the mouth, and then you see a microphone on top of that baffle, below the baffle. What this does is it separates the acoustics emanating from the nasal cavity from the acoustics emanating from the oral cavity. And if you measure the amplitude of, for example, the nasal microphone with respect to the oral microphone, then you get an indication of what the degree of nasality is. Importantly, for later on in this talk, it does this in a way that, unlike, for example, aerodynamic equipment, like a mask that you might wear to get nasal flow, this doesn't impede the acoustics at all. So if somebody is holding this on their upper lip, their speech sounds the exact same as if they weren't. So that's the nice thing about this. So what I did was, I was tracking degree of nasalization, also tracking shape of the tongue. And then I had these different phoneticians produce all of these different vowels around just different vowel qualities around the vowel space, and lower their velum. So things like e, o, ah, kind of thing, right? So try to keep their tongue as steady as possible, and then simply lower their velum over and over and over, get lots and lots and lots of data. So with that data, then, this is what the output of the nasometer looks like in Prot, for example. At the top here, we have the waveform for the nasal microphone, and at the bottom, we have the waveform for the oral microphone. And as you can see, at this point here, this is when the velum lowered, right? Because we've got primarily oral amplitude, acoustic energy radiating out of the mouth, and then somewhere around here, the velum lowers, and now you have energy radiating out of both cavities. Now, interestingly enough, look what happens to the formants. As soon as the velum lowers, you can see the formants shift, right? But you're probably saying, okay, well, they tried to keep their tongue as still as possible. How do you know they actually did that? Well, the formant shifting here could be just because they changed their tongue. It's actually really hard to do this. It's really hard. I was one of the speakers. It's really hard and tiring to do an experiment like this that's very contrived. So what I did was take all of the ultrasound frames within, so here I've automatically marked using the nasometry signal. So typically how this is measured is you take the nasal or the amplitude of the nasal microphone divided by the summed amplitude of both the nasal and oral microphones. So at the point where that ratio was the lowest, that is the most oral part of whatever this sustained vowel is. At the point where that ratio is the highest, that's the most nasal point. So I'm marking these for this token here. All of the ultrasound frames so the tongue configuration within that span of time from the most oral to the most nasal, basically take all of those frames, put it into one big matrix, and then do a principal components analysis on this. What this does is this gets a representation of the tongue shape, but all of the different dimensions are not correlated with each other. This is important because the next thing I did was take all of the ultrasound frames that are at the most oral part of the vowel, and then train a linear model, two different linear models for one for F1 and one for F2, essentially using these tongue PC scores, in other words, just a transformation of these tongue shapes to try to predict the F1, for example, or F2. Then with that model, this isn't really trying to predict, but this is more like building what the mapping is between articulation and acoustics. Importantly, when the velum is at its highest. So for a given speaker, what is the relationship between the tongue shape and F1 and F2 for this particular speaker for this vowel, right? Then, using that same linear model, use the tongue shapes in the most nasal portion of the vowel to try to then predict what should be F1 and F2 for that portion of the vowel. Then actually measure F1 and F2 and subtract the predicted values. The residual there then is the independent effect of velum lowering. You've taken away whatever the effect of the tongue shape is, even if they change the tongue shape slightly throughout this sustained vowel. All right, so that's the idea. Here are the results. So what I'm showing here, I've got all the different scatter plots here. And then I've got the sort of like opaque circles or the predicted observations, and then the sort of semi-translucent triangles or the observed observations. But importantly, these arrows are, they are connecting the mean values for each of these different vowel categories, each of these different vowel qualities. The arrow starts at the mean for what the predicted values are, and then points to where the actual the mean of the measured values, right? So essentially the arrows are pointing towards what the effect, the independent effect of velum lowering is. Okay. Now, what was really interesting about this is that I said, now hang on, this looks kind of familiar, especially this part of the vowel space looks super familiar to me. Actually, I'd seen something similar in my PhD thesis. So this is an article that came out of my PhD thesis, and in that I looked at the articulation and the acoustics of oral and phonologically nasal vowels in French. And here I've got the F1 and F2 value, well, the normalized F1 and F2 for, I think, the 12 speakers of French here. And if we sort of do the same thing, we draw an arrow from the oral vowel to the nasal counterpart, we can see, obviously, I mean, these are hugely different, right? These are not the same underlying vowel. But what's really interesting about this is that especially this part of the vowel space, where it's sort of these non-high, non-front vowels, this looks very similar to the acoustic effect of velum lowering. So the idea here is that, well, maybe over time, as French was developing from Latin to Old French to Middle French and so forth, as these nasal vowels were developing, perhaps it was the case that listeners heard the change in formants and then misperceived that as a change in tongue configuration, and then replicated new vowels with minor changes in tongue configuration, right? So that's the idea here. And I'm really especially interested in this main effect. So from this, this Jazza paper, the strongest effect, the most consistent effect, was a lowering of F1 for primarily for low vowels, really for all non-high vowels, but especially for low vowels, lowering of F1. Now, I'm not the first one to have found this. This has been predicted from modeling studies as well, that one of the effects of nasalization on low vowels is a lowering of F1. So we've got this really cool scenario where nasalization changes the acoustics. So low vowels in particular are acoustically raised, right? But there's been a lot of work on the perception, the relationship between the perception of nasalization and perception of tongue height. Turns out to be the case that low vowels, when they're synthetically nasalized, they're perceived as higher, right? And we've also noted diachronic patterns, that it's actually somewhat common when a language starts to phonologize vowel nasalization, there can often be sound change where low vowels are then eventually produced as higher with a raised tongue position, right? So there's this relationship here that sort of spans across synchronic effects of nasalization, but then also diachronic change. So then this points to, when I talked about at the beginning, speaker-based sound change versus listener-based sound change, something like this, really, because there isn't any, there is a muscular connection between the velum and the tongue. It's not very strong. That sort of relationship has been argued against for decades. So effectively, there really isn't any sort of physical constraint on the tongue and the velum acting independently or together or whatever they want to do. So this is, again, a case kind of like the alternation of labials and velars, where we think if this was the case, that these sort of acoustic effects led to the sound change patterns that we see historically, this is likely listener-based sound change then. There's a small problem with this. All these people that we would want to go back and bring into the lab and, analyze and take some data from them, they're all dead, right? So that's the end of my talk. Everyone's dead. There's nothing we can do about it. Except maybe there is something we can do about it. Linguistic time machine. So you're probably wondering at this point, what kind of people do they let through giving a linguistics degree at Western Washington University? Somebody talking about building a linguistic time machine. You can't do that. It's impossible, right? But I don't think it is impossible. If we rely on the fact that physiologically and cognitively, we are really no different. We haven't evolved that much from all written record that we've had language, right? So the sort of tool set that we have, the vocal tract that we have, the way that we can use the vocal tract in some sort of constrained way to produce speech, and also the mind that we use to process that speech is pretty much the same now as then. So the time machine that I propose is actually banking on that fact and trying to then recreate a sound change environment using people that are alive today, and then see how they sort of react to this. So how do we do this? The idea in general is that you identify some sort of sound change that we think is due or was due to listener misperception, right? So some listener-based sound change. And then you get two languages. What I'm going to call language A is some current language, which represents the state of language before that change. Then language B, some current language, which represents either the state after the change or as the change is ongoing. Importantly, these need to be distinct. One of them needs to be before the change has happened. Then speakers from language A who don't know language B, these are naive listeners, listen and imitate productions from speakers of language B. And then the question is, do language A listeners turned speakers exhibit evidence of articulatory misperception in the same way that we think historically was the case that led to sound change? So we're going to try this. We're going to take the time machine for a spin, and we're going to do this on what I've been talking about, vowel nasality and tongue height. Language A then is English, where vowel nasality is still phonetically contextual, right? We don't yet have a phonological nasal vowel system. French, on the other hand, does. So there is a change, right? Phonologization of vowel nasality. Language A hasn't happened yet. Language B, it's already happened. So language B first experiment put out in Journal of Phonetics in 2017 involved recording lots and lots of data from native French speakers, again, using ultrasound to get the tongue shape, nasometry to get a measure of nasalence, a separate microphone to get high quality audio. This is where it comes in the point I mentioned earlier, that the nasometry plate doesn't affect the acoustics. This is where this comes in key. And then something I'm not going to talk about today, but also EGG, electroglotography. So the reason why I measured this is because there are also really interesting correspondences between synchronic effects of nasality and diachronic change that are related to not to tongue height, but to aspiration and breathiness. So you get these cases of spontaneous nasalization that John O'Halla talked about, where in the historic record, nasalization comes out of nowhere, right? Except it's not out of nowhere. It still has a pattern. The pattern was that these cases were in the environment of some spread glottis sound. So I'm not going to talk about that today, but if you're interested, there's some really interesting findings that I got from that as well. But we're going to focus on the nasometry, the ultrasound, and the audio. So I collected all of that data from native French speakers saying real French words. You can see here on the screen, ils écrivent bout parfois. So bout is the target vowel here. And then in the second experiment, so I published that as a way of describing what all of the articulatory characteristics were between oral and nasal vowels, statically and also over time, and then what the relationship is to the acoustics. But then I took the audio from this high quality microphone, used and then excised the words, the target words, and then used those as stimuli for English listeners to then imitate, hook them up to all the same gear, right? The only difference is these participants are now wearing headphones, because instead of reading from a screen, they do have a screen here that they're reading just a list of words to get to normalize to their own vowel space for English. Anyway, and the idea here is that we have these 6 lexical items, and these are oral and nasal vowel counterparts. Again, I'm going to use air quotes here. I want to focus just on this pair, ah and on. Why? Because again, from the JASA paper, I found that the most consistent and the strongest effect was F1 lowering for low vowels. So this low vowel pair here, I'm especially interested, how do these imitators, when they are saying, they were asked to imitate as closely as possible what they heard, what is the relationship between their tongue position, their degree of nasalization, and importantly, F1 in comparison to the French speakers? So what I did is, like I said, nasalence is this ratio of nasal amplitude to summed amplitude of nasal and oral. And we can see that this is what this looks like. This is the word bon. And we can see we have a drop here, right as the pressure, the intraoral pressure builds up before the burst, and then and then it increases as nasalization starts somewhere into the vowel. Tongue height, I used, I think, edge track to track the shape of the tongue, and simply took after rotating to the occlusal plane, the highest point of the tongue, wherever that may be. And this was usually always, if not in all cases, somewhere on the tongue dorsum. And then F1 extracted Pratt using automated speaker and vowel optimized parameters. And then what we're going to look at, so the key thing here, is the difference in all of these measurements between randomly selected oral and nasal pairs, right? And then normalize those by speaker. And then I built linear mixed effects models to then test for group differences. So in other words, the measure that goes into this is what is the difference between oral and nasal, and is that difference different between the French speakers and the English imitators? Okay, so does it work? Does this time machine do anything? So again, we're just looking at this low vowel pair here today. First, I'm going to show you the F1 results. So the F1 results are the same. So what we're looking at here, again, these are differences for this low vowel pair. So I've drawn this horizontal dashed line at 0, where that is the exact same measure between the oral ah and the nasal ah. For both the speakers in red and the imitators in teal, F1 was lower for the nasal vowel compared to the oral vowel. And there is no difference between them. So with regard to F1, amazingly, the imitators were actually able to replicate the acoustic output, that characteristic of the acoustic output that the speakers had. But then nasalence, here we see predictably, now these are positive values, meaning the nasal vowel was more nasal than the oral vowel. That's not surprising, except not as much so for the imitators. So there's a significant difference here that the imitators, even though they produced the same F1 value, they produced the nasal vowel with a less great of a difference in nasality compared to the oral vowel, compared to the French speakers, if that makes sense. Okay. So then you're probably all wondering, what about tongue height? So tongue height, first of all, there is a significant difference between the speakers and the imitators in this direction. So the speakers had a lower tongue position for the nasal ah compared to ah than the imitators did. But importantly, you can see that these are sort of hovering around 0. And a post hoc test revealed that actually both of these were significantly different from 0. This is really important. What this means is that the French speakers produced the nasal ah with a lower tongue position, not hugely so, but statistically significant. A lower tongue position than the oral ah. However, the imitators produced a higher tongue position for the nasal ah compared to the oral ah. Precisely what we think happened in the development of nasal vowel systems, for example, like in French or Portuguese, where you see this sort of raising of of low vowels when they become nasalized. But the difference is we were able to capture this sort of in more or less real time in the laboratory. So I think it works. So I have SF here because these were specifically, it's not really important for this talk, but these were Southern French speakers. They produced the nasal on with a lower F1, even though the tongue was lower, which is predicted to raise a F1. So this lowered F1 relates back to what I found as the independent effect of velum lowering, that this lowered F1 is not due to tongue height, but due to nasalization. However, these imitators produced less nasalization and a higher tongue position to get the same F1 output. So the proposal here is that I recorded this data in Sydney, so the AE here is not American English, but Australian English. The Australian English imitators at least partially misinterpreted the cause of F1 lowering as being due to tongue height instead of nasalization, and then reanalyzed their articulation accordingly, sort of on the fly as they became listener turned speaker. So the listener turned speaker here produced a micro sound change on an individual level in the exact same way that has been argued to have occurred for macro sound change on a community level in various languages. So the conclusion here is that indeed, for some sound changes, at least for this relationship between tongue height and vowel nasalization, listener misperception is a very probable mechanism as a catalyst for sound change involving tongue height and nasality. So is this support for listener-based sound change? Yeah, I think it is. So the idea here is that we have nasal flow that has these acoustic effects. We have the oral sort of radiation that has these acoustic effects. And what the listeners hear then is the combined again, the conflation of the acoustic effects of both of these tracts. And then sort of there's this cue weighting that happens where they attribute at least some of what they're hearing as being due to the oral tract alone. So I said that this is an ongoing research for me. And so what are the next stops for this linguistic time machine? Well, as I mentioned at the beginning, velar labial alternations is another type of sound change that we think, well, must have been due to listeners, right, in some way. So I have another example. I gave examples from Proto-Indo-European, but here's an example from Proto-Bantu, where we have this same sort of alternation where velars then eventually become labials. So the idea here, language B, the speakers, would be Spanish speakers, where we can get both labialized and non-labialized velars and labial sounds, right? And then getting, as language A is the imitators, again, English, using an EMMA study to then track both lips and tongue. And the idea here is, does the labialized environment then lead to more substitutions, these velar labial alternations? This is the idea, is that if this is indeed due to listener misperception, then we predict that this would be the case. That these, I don't speak Spanish, so this can be horrible, but these examples like cuento, well, I would slice part of the vowel out, so you wouldn't have the whole word here, but the environment of like cuento versus que, puesto versus pe, that those would happen for cuesto or cuento and puesto, but not the non-labialized, or not as often with the non-labialized. Also, this sort of listener-based sound change has been argued not just as at a feature level. So here we've been talking about everything at a feature level. Somebody hears features or whatever the acoustic effects are of one feature, and then it misattributes them to some other feature, right? This has also been argued to happen temporally. So in some cases, metathesis has been argued to also be listener-based, or at least listeners play some key role here. So there's a sound change in progress in Andalusian Spanish of metathesis of consonant aspiration in particular. So words like bata, what used to be pronounced bata, are now pronounced by some speakers as bata in some cases. And importantly, many younger speakers do both. So this is a sound change in progress where their parents and grandparents would only do pre-aspiration. These speakers, these younger speakers are doing both. So this is an example where language B is a sound change in progress. This is important because, or it's a sound change A is a sound change in progress. This is important because these speakers can do both of these things, right? This is not the case for English. So English aspiration is it's highly predictable when it occurs and not. So the idea behind this is to use modified nonce words like spata, where the p would not be aspirated, but the t would be, and then excise out just the pata part, and then use these as stimuli to then play to Andalusian Spanish imitators to see then if these cases can be then reanalyzed as they're imitating. And the last one, actually, I'm sort of most excited about, and one that I want to run first, is an extension of the current research that's quite a bit different. So language A and language B are actually the same speakers. How the change then would happen is real-time speech perturbation, where there's processing that's done with very low latency, so essentially immediately on the fly. That's done to somebody's own voice, and then what they hear is a slightly modified version of their voice, right? And so there's been lots of research to show that when you do this, for example, by changing vowel formants, people then change their vowel quality. If you do it with pitch, people change their pitch, and lots of work that's been done on this. So what I would like to do is then two different real-time speech perturbation studies, basically hook everyone up to the same equipment again, and then in one study, modify F1. So slightly change F1, decreasingly over time, and then see how the speakers modify their articulation. Do they change their tongue position? This has been shown for formant perturbation in previous studies, but it hasn't been done on in conflation with vowel nasalization. So what I'm curious to see is if speakers change tongue position as they hear their F1 changing, or as we know now, F1 can be changed due to nasality as well. Do they change their degree of nasalization? Or do they do both? Do they sort of reweight their entire articulatory strategy in an act of compensation? The other thing that I want to do then is, again, a nasometry device is just these two different microphones, and they are more or less full bandwidth microphones. You listen to audio that's recorded on these, and it sounds pretty good. So what I would like to do then is also do speech perturbation, but take the two microphone signals, collapse them together as a monaural signal, and then play that back to the speakers. The perturbation would then be, before they are made monaural, changing the amplitude. So what this would do is change their own perceived degree of nasalization and all of the acoustic effects that come along with that. And then to see, again, do they compensate by changing their degree of nasalization? So if I increase the nasalization, do they decrease? If I decrease the nasalization, do they increase? Or do they also change their tongue configuration, even though I haven't done anything with their tongue? And now, thank you, and say that this is the end of the talk for real this time.